Dear friends of Future in Medicine, welcome to this very special edition of the Future in Medicine Science Match, which is also the first edition of Future Medicine for me as new CEO of the BIH. We are, of course, very pleased that we can hold this conference again this year, albeit under completely different conditions and prerequisites than in the 4 years before. The Future Medicine Science Match, which the BIH has been hosting together with Tagesspiegel since 2016, is so popular because it regularly hosts over 800 international participants from science and industry, from clinical and health professions, from politics and startups, meeting and discussing the scene, creating common ideas, collaborations and projects. This year is different, as you well know. Like many other events, we had to give in to the virus and relocate future medicine to the internet. Thematically, it's still perfectly fitting because we are dedicated to artificial intelligence in translational medicine. The reason for this is that in modern medical research, but also in the examination and care of patients, so immense amounts of data are being generated that they can no longer be managed with human intelligence alone. And because the Berlin Institute of Health has, among other things, taken up the case of the digitization of medicine, we look forward to the many contributions from very different areas of research, development, or application in which artificial intelligence is already finding its way and which we are presenting to you online this year. Importantly, we have retained one characteristic of future medicine, which, in addition to the many participants, is the basis of its great attraction: the brevity of the contributions. All speakers have to get to the heart of their research, product, or idea within 3 minutes. You, dear participants, had the opportunity in advance to vote who met best this challenge. You will find out at the end of the event who has become the audience's favorite. Finally, let me say a few words of thanks. Sylvia Thun, BIH Professor for eHealth and Interoperability, is the scientific director of this year's conference. I would like to say thank you to her personally. Also a big thank you to Ms. Knoll from Tagesspiegel for choosing us again as a partner this year. Many thanks to the organizational team led by Julia Richter at Tagesspiegel and Susanne Wehring at BIH, who have made sure that we will have almost as much fun online as in previous years offline. And of course, thank you to everyone who went looking for good speakers. That was, next to Sylvia Thun, Petra Ritter, Johanna Quandt Professor at BIH and Charité, and Roland Schwarz, Group Leader at the Max Delbrück Center for Molecular Medicine, the MDC. And now, I wish all of us a lot of fun, good entertainment, and many novel ideas for joint co-working in the 5th Future Medicine Science Match on Artificial Intelligence in Translational Medicine.
Sehr geehrte Damen und Herren, ich freue mich sehr, Sie zum Future Medicine Science Match begrüßen zu dürfen und glaube, dass Corona ein echter Booster für Digitalisierung gewesen ist. Denn bei vielen IT-Projekten haben immer wieder Bedenken die Runde gemacht, wie schulen wir eigentlich unsere Leute, was mit dem Datenschutz, was machen wir, wenn das irgendwie nicht funktioniert, kapiert es auch der Letzte. Und wir haben gelernt, auf einmal durch Corona über Nacht sind viele digitale Dinge möglich geworden, über die man vorher jahrelang ohne Ergebnis diskutiert hat. Und ich glaube, das ist gut und das müssen wir auch nutzen, denn nirgendwo wird die Digitalisierung auch mehr gebraucht als im Gesundheitswesen. gigantische Einsparpotenziale, die es hier zu bergen gilt, besseres Wissen und Lernen, indem man mit Datenanalysen besser Krankheitsverläufe und auch deren mögliche Ursachen versteht. Und deshalb begrüße ich die vielen Initiativen unserer Kollegen im Bundesgesundheitsministerium einmal sehr, die gerade jetzt in dieser Periode auch besonders Jens Spahn als Minister beherzt zugegriffen haben, um hier angefangen von dem Thema der elektronischen Patientenakte eben bis zur Abrechenbarkeit von Gesundheits-Apps doch sehr viel für das digitale Gesundheitsökosystem zu tun. Und wir als Bundeswirtschaftsministerium flankieren das an verschiedenen Stellen. Wir haben zum Thema Digitalisierung in der Gesundheit auch im Konjunkturprogramm Dinge miteinander verabredet. So machen wir beispielsweise auch einen Förderaufruf zum Thema künstliche Intelligenz in der Gesundheit. Und ich glaube, dass wir hier riesige Potenziale haben, an denen man jetzt engagiert arbeiten muss. Wir sollten den Schwung durch Corona mitnehmen, indem wir sagen, es ist notwendig, was zu tun. Es ist erfolgreich in anderen Bereichen gewesen. Lasst uns die Ärmel hochkrempeln und Gas geben. Daran arbeiten wir mit großer Freude mit und wir wünschen Ihnen heute für Ihre Veranstaltung alles Gute, gute neue Erkenntnisse, Vernetzung und vor allen Dingen, dass wir dabei ins Doing kommen.
Ladies and gentlemen, I'm proud to welcome you to the Future Medicine Science Match 2020. We have so far experienced a truly crazy year, a year full of enormous challenges. A year that has demanded a huge amount of energy and flexibility from all of us. And quite frankly, which starts to get on our nerves. We are all the more pleased that you are here with us today to talk about the future of medicine. What can be more important than a topic like this? This will be an exciting day. Berlin's premier newspaper, der Tagesspiegel, together with the Berlin Institute of Health, the Charité, and the Max Delbrück Center for Molecular Medicine have assembled a truly amazing group of the most innovative international experts in their fields. We have in our conference scientists, physicians, healthcare experts, researchers and politicians, developers and innovators, entrepreneurs and investors. And that despite the difficulties that COVID-19 has imposed on each and every one of us. I'm also pleased to welcome Federal Research Minister Anja Karliczek. And I welcome Thomas Jacombek, the Commissioner for Digital Economy and Startups in the Ministry of Economic Affairs, who worked non-stop to navigate us through these pandemic times, and still he made it. Thank you for finding the time to join us here at the Future Medicine Science Match. One thing is for sure, while the pandemic is changing the world, there's no better time to strengthen the commitment to science with an event like this and to organize a platform for researchers to show us new perspective of medical research and development. For the fifth time now, we are bringing together some of the brightest minds and most exciting scientific developments at Future Medicine as part of the Berlin Science Week. Everything that we are going to see and hear today, I guarantee you, will amaze us. But it also meant to stimulate a discussion about what science and innovation can contribute to the future of medicine. I look forward to the pitches which are being presented to us today. The fact that all of you are taking the time to attend Future Medicine online instead of on site as you used to do it in the previous years shows once again that Berlin is the top address for worldwide research and for international networking. And that makes me proud. This is a great confirmation for our universities and for our research institutes, and of course for the attractiveness of our city. At der Tagesspiegel, we are accompanying constantly the developments in Berlin as a city of science. My colleagues from our science department write daily about life sciences and how they are changing society. And so I'm now all the more excited about all the projects and ideas which will be presented to us today, especially in the field of artificial intelligence. Let me conclude by thanking all those who have made this great event possible. There's the Berlin Institute of Health team led by Professor Sylvia Thun, Professor Petra Ritter, and Dr. Roland Schwarz, who ensured the scientific depth of the Future Medicine 2020. And I would also like to thank Stefanie Zeltmann, the head of communication and marketing of the Institute, and Susanne Wehring, the event manager of the Institute. And I would like to thank you, the Tagesspiegel team around the publishing director Susan Knoll, with director Julia Richter on her side, and Rabea Rehmer-Zirkel, Stefanie Lassack, Angie Leps, Emma Daubers, Paula Landmesser, Carlotta Rupert and Ulrike Stadler. Together, they all contributed to the success of this event. And if we would be live, and we would sit together right now, we would give all of them a big applause. And now, ladies and gentlemen, enough talk. I wish you many new and useful insights at the Future Medicine Science Match. Enjoy the day. Thank you very much.
Welcome to the Future Medicine Science Match 2020. The focus of this year's virtual summit is artificial intelligence in translational medicine. In the next 2.5 hours, we will meet top international scientists presenting their work, their achievements, their visions in very short talks. We will discuss together with you what the big impact AI project in future medicine should look like, must look like, and we will award 2 prizes for the best pitches. The virtual summit is hosted by the Tagesspiegel and the Berlin Institute of Health. My name is Monika Seinscher, I'm a science journalist, and it is my pleasure to welcome my co-host for today. Professor Sylvia Thun is IT specialist for medicine and director of e-health and interoperability at the Berlin Institute of Health. Professor Thun, you were one of the chairs who were involved in the science preparations of the Future Medicine Science Match. What are you expecting? What are you hoping will happen today?
Today we get introduced to the latest technologies, and we will be part of a worldwide community who work together on innovative, interoperable and secure solutions. Scientists will give us an exciting insight, and we will dive deep into algorithms, and we will learn a lot. The scientific question is, can AI and translational medicine help to fight the COVID-19 pandemic and improve patient care?
Thank you. We will talk again later this afternoon, and I'm now pleased to introduce our opening keynote speaker. Pavel Svoboda is Director General of the Human Brain Project. Hello, Mr. Svoboda.
Yes, hello. Very good afternoon.
You will be talking about powering a new era of brain research with for artificial intelligence. Mr. Svoboda, what can the brain and AI learn from each other?
Excellent question. Thank you very much for having me today. I'm delighted to join the Future Medicine Science Match in Berlin. And let me say straight out that we are at the cusp of a new era in brain research. And this is because unprecedented technology is now put at the service of science. Many neuroscientists among you will remember studying the firings of single neurons. And it feels like yesterday. It was yesterday. From single neurons, the field went to populations of neurons in different regions of the brain. Today's research spans multiple scales in space and time. So it's a completely different world. Nobel Prize winners such as Edward Moser call this a revolution in neuroscience, because technology suddenly made possible to record simultaneous activity from thousands of neurons with known connectivity. All this can now be done in cellular resolution and over duration of long behaviors. Of course, many questions remain to be answered. That's why it is so fascinating to be in this research now. For example, how does the activity of the neurons lead to high-level brain functions, such as memory, planning, or thinking? How does the brain switch from using one set of recurrent neural networks to another? Or what's the role of the brain also in the evolutionary context? Is it to explain the worlds in which we find ourselves, or help us survive and make the most out of it? So these are some of the questions that I think many of researchers are struggling with today. In a taste of most recent discoveries, Human Brain Project scientists have proposed that different subnetworks process information in the brain at different speeds. They call them the slow updating network, the SUN, and the fast updating network, the FUN, with multi-storage core that belongs to both of them. Such discoveries help us know more and more about the brain. And understanding high-level cognitive functions is at the heart of understanding the course of diseases, where these functions are compromised. eBrains, the project I have the privilege of co-leading with our distinguished scientific team, will be a top-level enabler to address these challenges, making the most of the technological revolution that I mentioned. eBrains, to decode the term, stands for European Brain Research Infrastructures, and it is unlike anything else in the world because it aims to go deeper into the brain and wider across the scales, and it is entirely co-created with the researchers. So eBrains is a digital infrastructure at the interface of neuroscience, computing, and technology, including AI, and I will come back to AI in a second. It is a major outcome of the Human Brain Project, one of the world's largest scientific programs to study the brain, which runs until 2023. So what difference does eBrains make? Let me answer this question. So it is a one-stop shop offering scientists and developers the most advanced tools and services for brain research. From the knowledge graph, the data sharing repository, helping the scientists find and share data they need to make their next discovery, through data curation, next generation brain atlasing, onto modeling and simulation platforms, and AI-based analysis. So instead of going to different places, which you would normally have to do, you will now be able to come to eBrains and get a package of tools at once. This will be the most comprehensive set of services available anywhere for multi-scale brain research, with a service provision that is curated for the individual needs of researchers. Let's take the example of brain atlases, where we link cellular data with data on other aspects of brain organization in an unparalleled fashion. The Unique Brain, part of eBrains, is the first 3D atlas of the human brain, showing the variability of the brain structure with microscopic resolution. Most atlases today offer a resolution in the millimeter range, and they do not allow scientists to obtain information about thin fiber bundles, cortical layers, microcircuits, or cells. This is why we need to go deeper. And our scientists in Human Brain Project, together with partners at McGill University, are now aiming to develop a brain model with an accuracy of 1 micrometer and processing several petabytes of neuroscientific data along the way will be necessary. eBrains empowers the community to use exascale computing, take advantage of powerful high-performance analytics powered by a network of European supercomputers with a full spectrum of specialized services. So what difference do we aim to make through this infrastructure? In the area of medical applications, this is about diagnostics, it's about surgery, prosthetics, and drug screening. Neuroimaging, in combination with the eBrains multi-level atlases, provide a key support for diagnosis and therapy planning. Such tools will help to interpret the results more accurately and lead to better guided interventions in patients' brains. Physicians will be able to craft personalized brain models. eBrains would also allow for developing better software for deep brain stimulation in patients with Parkinson's. Microstructurally plausible information on target brain regions could help in the surgery of brain tumors. One example of which we are particularly proud is the epileptic virtual patient. The epileptic virtual patient uses the state-of-the-art virtual brain simulator available through eBrains to develop patient-specific individualized brain models to help improve surgical outcomes for epilepsy patients who cannot be treated with drugs. There is a sizable group of such patients. A clinical trial of this technology is now ongoing and planned to end in 2023. Another example is a project aimed at restoring vision in blind people using electrical stimulation of the brain. Peter Railsema and his research group in Amsterdam use eBrain's atlases to ensure they target the right part of the visual cortex. So this is a project that will develop a prosthesis with thousands of electrodes driven by adaptive machine learning algorithms, helping millions of people with impaired vision. eBrains is also about access to clinical data, which is essential for therapeutic advances. The eBrains medical informatics platform, currently installed in over 30 hospitals, allows for creating robust profiles for brain disorders, including rare diseases, and for benefiting from the statistical power of a sizable combined volume of clinical data. We are also preparing right now a system of secure sharing of data. We want to become part of the EU-driven project on building a European health data space, something which is, of course, essential for the future development of therapies. Today's advances would not be possible without the support of artificial intelligence. In fact, brain research has a completely synergetic relationship with AI. Unlike many other disciplines, this is about a two-way street, meaning that it will greatly benefit from AI tools, but it will also pay back, so to say, by contributing to development of AI in the future. AI is particularly well suited for addressing the complexity of the brain, which is unparalleled with 86 billion neurons, each with thousands of connections with other neurons. The amount of data in single images and the complexity of that information is such that no scientist can analyze them on her or his own. So brain research desperately needs artificial intelligence and its pattern recognition functions. And eBrains users benefit from deep learning algorithms for segmenting brain regions in high-resolution scans of brain tissue. There are also specialized treatments adjusted to patient specificities. Monte Carlo Markov chains techniques are used in epilepsy surgery, and big data analysis are helping to identify disease markers, and Bayesian inference is used for brain activity analysis. But it is a two-way street, as I said, two-way relationship, because AI still has plenty to learn from the brain. Both brain and current artificial intelligence are recurrent, but they are recurrent in different ways. AI relies on single recurrent neurons and lacks the dynamics of the brain with its bidirectional connections, with the feedback loops, which pass the information in reverse direction. So there is therefore a lot that AI can still learn from the brain. One of excellent examples of how this synergy works is the learning algorithm developed earlier this year by the Human Brain Project scientists led by Professor Wolfgang Maass. Integrating learning into mobile hardware could do a lot to save energy and remove one of the biggest hurdles for broad use of artificial intelligence. It is worth recalling that the brain only needs 20 watts, and this is a millionth of the energy of a supercomputer. So scope for brain-inspired solutions is enormous, and that's why it's really a two-way street, a two-way relationship. So let me finish by saying where eBrains wants to be in the future. We will want to be much bigger in the area of public health and medical applications. And this is really a call to action that follows directly from the fact that 179 million Europeans suffer from a neurological condition. And in the midst of the COVID-19 pandemic, we clearly now have a mental health pandemic. So the urgency of addressing these issues is enormous. And we are committed to developing e-brains at the service of brain medicine. We could not do otherwise. We would like to be an important actor in developing the future European partnership for brain health that is likely to emerge in the next few years on the European scene. This means that our tools can and should be taken to a new level as well, helping to better understand and manage behavioral or emotional dysfunction, develop predictive models in mental disorders, or derive concepts for language learning and language therapy. And we are looking at those plans right now very intensively. So concluding, it is sometimes said that brain research is a bit like physics in the 19th century, namely ahead of its most important breakthroughs. Technology today offers us unparalleled opportunity to develop a set of principles that will explain how the brain functions. And this can be overwhelming and intimidating, or it can be thrilling and fascinating. And my plea today is to treat it as a fascinating challenge, as a fascinating journey, helped by technology and helped by artificial intelligence in particular. Thank you very much.
Thank you, Mr. Swoboda. I'm wondering, where do you see the biggest challenges in this vision of the future that you were just talking about? What is the biggest main issue?
Well, there are challenges in the study of the brain and in understanding of the brain. And as I said at the end, the feeling very often is that brain research is like physics in the 19th century, so it's still ahead of the big discoveries. So these have to do with understanding the brain functions. These have to do with understanding how the brain moves, uses one network of neurons or the other, and how it switches from one to the other. And all that is, of course, important for developing diagnosis and treatment. So we have to do both. We have to deepen our understanding of the brain. And of course, we also have to look after some of the low-hanging fruits, some of the improvements in the therapeutics that are already possible on the basis of our knowledge as it is today. I mentioned the scale of the phenomenon in terms of the health challenge: 179 million Europeans with a neurological condition. That covers a broad spectrum, of course, of diseases from migraine onto Alzheimer and Parkinson. I think this is really a call to action for us. And we need to move in a parallel way, deepen our understanding of the brain, but also do as much as possible in therapeutics on the basis of the tools that we currently have at our disposal.
Thank you very much, Mr. Swoboda, for this thrilling keynote. And now we come to the core element of every future medicine science match, to the pitches, where young scientists present their work in only and exactly 3 minutes. From the many participants on our website, on our platform, a jury of 3 senior scientists chose exactly the 14 best pitches to be presented today. And the pitches were grouped in 3 sessions, each of them chaired by 1 member of the jury. And the first session of pitches combines pitches about artificial intelligence and basic medical research. Its chair is Dr. Roland Schwarz. He's group leader of evolutionary and cancer genomics at the Max Delbrück Center for Molecular Medicine at the Helmholtz Association. Good afternoon, Dr. Schwarz.
Hello and welcome to the first session of Future Medicine 2020 on AI and basic medical research. Basic medical research forms the foundational building stone of translational science and aims at understanding the biological underpinnings of disease. It thereby draws on many different technologies, from cell lines to model organisms to imaging, multi-omics, and epidemiological methods. Like in many other areas, machine learning, data science, and artificial intelligence have truly revolutionized the way that we think about health research data. In cancer research, for example, Machine learning can now help to understand and predict the evolutionary processes that are shaping these cancer genomes. It can also help to predict the effects of individual somatic mutations. In neuroscience, complex brain simulations have been developed that help to understand the effect of germline variants on neurological information processing. Machine learning also helps to extract features from medical imaging data, for example, or help scientists to better understand the results of large-scale sequencing cohorts. There, we're now moving away from large sets and lists of genes towards a more coherent biological interpretation of the results using machine learning methods. As you can see, the potential applications of AI in basic medical research are vast, and I'm very excited to have a fantastic set of talks for you today. And so without any further ado, I wish you a lot of fun in this upcoming session on AI and basic medical research in Future Medicine 2020. Thank you.
Thank you, Mr. Schwarz. And now we start with the first pitch by Teresa Krieger from the Berlin Institute of Health. And please, Mrs. Krieger, you've got exactly 3 minutes, and I'll interrupt you after 3 minutes. Please.
Hi, and thank you very much for joining. I'm going to talk about cellular heterogeneity and drug response in pancreatic cancer, which is work that I'm doing in collaboration with colleagues in Berlin and Heidelberg. Next slide. We're looking specifically at pancreatic ductal adenocarcinoma, or PDAC, which is the most common type of pancreas cancer, and is also predicted to be the second leading cause of cancer mortality by 2030. And this tumor, when it's diagnosed, is mostly not resectable, and there's variable outcome to chemotherapy that we see in the patients. And this is despite recurrent genetic alterations that occur in most of these tumors. So the question is, why are outcomes heterogeneous? And we wanted to look at this at the transcriptional level. Next slide. So to do that, we derived pancreatic cancer organoids from 18 patients, kept them in cell culture, and then subjected them to single-cell RNA sequencing and to an imaging-based drug screen, and analyzed the results using different machine learning methods. Next slide. What you can see here is an integrated depiction of more than 90,000 cells from these organoids, and you can see that we identified different clusters of cells, a number of clusters of proliferating cells that go around the cell cycle, 2 clusters of differentiating cells with pancreas-like functional traits such as secretion, and 2 clusters of immune and auto and paracrine signaling cells, and also the genes involved in these processes. Next slide. It's been known for a few years that there are 2 transcriptional subtypes of PDAC. That's the classical subtype that has more mucinous features and longer survival, and the basal-like subtype with a worse prognosis for the patients. And we found that in our cohort, these 2 subtypes actually coexisted in some of these patients. And the heterogeneity was related to poorer prognosis of the original tumor. Next slide. So what actually came out of the drug screen, I've summarized here in this figure. And the red values basically mean high values and blue means low values. So you can see that the more classical tumors have a lower proportion of cycling cells and have a better response to drugs. So the drug screen basically links the responses that we see with the PDAC subtypes and the level of differentiation in vitro. And quite interestingly, these results that we saw in the dish were consistent with clinically observed patient outcomes. Next slide. So what I hope I could show is that we've devised a functional approach to study cellular heterogeneity to identify compounds that could improve patient outcomes using machine learning to analyze in vitro biomedical research results. And I'd like to thank our collaborators, our funders, and thank you very much for your time.
Even 30 seconds early, that's perfect. And the next pitch is from Max Schubach, Berlin Institute of Health. Please.
Hello, everybody. In the next 3 minutes, I would like to show you how we use deep learning to understand the regulatory mutations for common and rare diseases. Hope my slides going to be online soon, but as you know, every cell in our body shares the same copy of DNA. But in contrast to that, the cells itself look very different. We have different types of tissues like heart, the skin, or the bones. So here, regulation of the DNA plays an important role for the differentiation into these different tissues. So around 50% of the human DNA has its own regulatory property. So here proteins can bind to it, activate or decrease the transcription of genes. Mutation in this part of the genome can also cause genetic disease. But in the past, they have most been overlooked because they are really difficult to judge. Next slide. So we will use now a deep convolutional neural network to, next slide, please. We use a deep convolutional neural network to train this, to predict these regulatory effects. And we use a similar approach like for pictures, where I have these 3 colors, but now we have our 4 nucleotides, and we feed it with the regulatory sequences of different sequences for different cells. And these convolutional filters, they will predict patterns of regulatory property. Next slide. Our model compared best to other predictors. Next slide, please. We tested on regulatory effects of experimental data, but the problem is that these data is really limited. Here, most is done is just in one single tissue, or it's just one spot in the genome and it's not genome-wide. So we thought we need new data. Next slide, please. So we did our own experiment using massive parallel reporter assay, where we designed 170,000 mutations and predict the effects in 4 different cell types. Because it's difficult to select these mutations in the genome, we used our trained model to select good candidates for our assay. So we recently concluded the experiments, and after the analysis, we have done a direct feedback to our deep neural network. So hopefully with this data, we have then now an unbiased training set for machine learning, where we can now predict regulatory mutations better. This is a really critical step forward for the interpretation of genome-wide mutations in common and rare disease. Next slide. I'd like to thank you for your virtual attendance and all the people that contributed to the work. Thank you.
Thank you very much, Mr. Schubach. And that applause was also for Mrs. Krieger, which we lost on the applause. The next pitch is from Sören Lucassen, Charité Universitätsmedizin Berlin. Please, it's your turn.
Thank you very much. I would like to present our project on gene set inference from large-scale single-cell expression data. And genes typically don't act alone, but rather they elaborate in a context that is set by variables such as cell type, disease state, or treatment. And to basically deconvolve this context, we developed a deep learning-based tool. Our architecture is based on that of autoencoders, which is a type of deep neural network that compresses and decompresses data, which is typically unsupervised, as we just try to train for the output to be as similar as possible to the input. We modified the architecture so we can feed metadata, such as cell type, disease state, or treatment, into the latent space, that way forcing a certain encoding of the information. Because we know exactly how the information is encoded in this latent space, we can then inspect the decoder network to see how it uses this data to reconstruct gene expression from the encoded metadata. Starting from a single neuron in the latent space, we can trace its weights to the next layer to see how it positively or negatively affects regulation of the next layer and any further layers until we finally reach the gene expression layer. Since the hidden decoder layers are still compressed, we we'll see neuron sharing between different types of metadata, thus identifying metadata specific as well as shared gene sets. Note that because we are only tracing the weights and basically doing a random walk on them, we're not actually predicting gene expression, but rather we are looking at the potential for expression. This is quite similar to the way a transcription factor would work, which we would still consider a repressor even if its target gene in a certain tissue was already off. Traditional methods would rely on gene set inference for certain types of metadata or covariates by regressing out all our other variables. The advantage of our method is that we can look at different covariates at the same time and call gene sets for them simultaneously but separately. Yes, and with this, I would like to, I maybe should mention that we call this restricted latent variational autoencoder, or RESVA. So if you Google this, you will find our GitHub repository for the code and our bioRxiv preprint. And with this, I'd like to thank all the people involved and you for your attention.
Thank you, Mr. Lucassen. The next pitch is by Christian Stephan from Kairos GmbH. Please.
Yeah, thank you for the kind introduction. My name is Christian Stephan. I'm the managing partner of the Kairos company who provides software solutions for healthcare and research. So please, next slide. So each day, 9 people are dying in road traffic. And some days ago, 40 people are dying each day on Corona. But we have today, while we talk, 160 people every day who dies on sepsis. And this is a problem because the physicians do not know why this happened. Who will survive and who will not survive is a problem why we try to gather with this project. Next slide. So we have this project called Sepsis DataNet, and we collect data, intensive care data, from clinics over the state. These are 8 clinics, and we use this data to build up a prediction model. And you see on the right side that we have this prediction model very well, and we can tell who or which people will survive in the next 30 days and what are the features why they survive, and we can collect these data. So please, next slide. But the problem is as well, if they leave the clinic and survive any kind of these sepsis, they have these positive effects too. And within the first year, 35% of these people who survive the sepsis will die within the first year. And again, we do not know why. And this is why we start, the next slide please, a project again, who's called DINA. And this will a digital follow-up of sepsis patient. We would like to collect these data in a residential environment, implement again an AI-based prediction model to prevent relapses before they occur or at least deaths. So please, next slide. We need 5 components to do so. So the first component is the acute phase of the sepsis, and we already have by this Sepsis DataNet project. But, next slide. We need as well data coming from the history of these patients. And this will be hopefully provided by health insurance companies for the diseases, the medication, the surgeries. And, next slide. We need these data as well coming later on after they leave the clinic, again from the health insurance company, but pseudonymized. What we also try to collect is data by questionnaires who we raise to the patients, and we will use an in-ear sensor to collect acute data directly from the patient to build up, next slide, at least the data integration into one center to build up again a model for also predicting survival of these patients in the first year, and to have at least a dashboard for physicians as an early detection system for these physicians to have an even better care of these patients in the future as well. So, next slide. Thank you for your attention. Hopefully there will be time to raise questions to the speakers later, and enjoy at next the speak of Mrs. Karliczek, I guess. Thank you.
Thank you, Mr. Stephan. You already made the announcement of the next speaker, but before that, I would like to thank you and all the pitches from the first session. We will see you all again afterwards at the end of this summit during the awards ceremony. And there will be certainly the possibility to ask questions during the networking event afterwards. So you're very welcome to join that one and stay online after the summit is over. But before that, I would like to mention that the Future Medicine Science Match is now in its 5th year. And from the very beginning, the Federal Ministry of Education and Research was with us, and we are very thankful for that. And so I'm happy to announce that Minister Anja Karliczek will enrich our conference today. We were able to do a short interview with her in advance, please.
In der Medizin der Zukunft wird künstliche Intelligenz eine ganz wesentliche Rolle spielen. Sie wird uns helfen, individualisierte Therapien zu entwickeln, zugeschnitten auf jeden und jede Einzelne. Mit Hilfe von künstlicher Intelligenz können wir das komplexe Zusammenspiel ganz unterschiedlicher Faktoren viel besser verstehen. Ernährung, Bewegung, Arbeit, Alter, Geschlecht, Gene. Sie alle können Einfluss darauf haben, ob ein Mensch zum Beispiel an Diabetes oder an Krebs erkrankt. Künstliche Intelligenz hilft also in zweierlei Richtungen, um Krankheiten besser vorzubeugen und Therapien sicherer und wirkungsvoller einzusetzen. Außerdem, künstliche Intelligenz kann beim Operieren zum Einsatz kommen, etwa bei anspruchsvollen Eingriffen unter dem Mikroskop. Per Sprachsteuerung können Ärztinnen und Ärzte wichtige Informationen anfordern, die im Okular des OP-Mikroskops erscheinen. Und zuletzt noch ein Beispiel, das in der aktuellen Pandemie für Covid-19-Erkrankte hochrelevant ist. Eine App, die mit der Medizininformatik-Initiative des Bundesforschungsministeriums entwickelt worden ist, die überwacht die Vitaldaten von Patientinnen und Patienten, die auf Intensivstationen beatmet werden müssen. Und die App erkennt in den Datenströmen Vorboten eines akuten Lungenversagens und sendet dann sofort einen Warnhinweis. Und so gewinnen wir wertvolle Zeit, um lebensrettende Maßnahmen schnellstmöglich einzuleiten. Zum Beispiel bei der Auswertung von medizinischen Bildern. Ein Beispiel aus der Nationalen Dekade gegen Krebs. Bei der Erkennung von schwarzem Hautkrebs haben Forschende aus Heidelberg in einer Studie künstliche Intelligenz gegen Hautärzte antreten lassen. Und die KI hat sich sehr gut geschlagen. Die Studie konnte zeigen, dass künstliche Intelligenz eine sehr sinnvolle Unterstützung sein kann. Und noch ein Beispiel aus unserer Medizininformatik-Initiative. Hier haben Forschende zusammen mit Industrieunternehmen innovative digitale Lösungen entwickelt, um mit Hilfe von künstlicher Intelligenz die Angaben aus Befunden und Patientenakten besser nutzbar zu machen. Und dafür wurden Methoden der Sprachwissenschaften mit Methoden der Informatik kombiniert. Ausgestattet mit künstlicher Intelligenz sollen Computer lernen, aus den ursprünglich von Menschen für Menschen geschriebenen Texten wichtige Informationen herauszulesen. Und so können Ähnlichkeiten zwischen Behandlungsfällen schneller identifiziert und eine Erkrankung damit auch schneller diagnostiziert werden. Die Bundesregierung fördert künstliche Intelligenz vor allem im Rahmen ihrer KI-Strategie. Mit der KI-Strategie fördern wir Forschung, Entwicklung und Anwendung von künstlicher Intelligenz massiv. Wir haben 3 große Schwerpunkte gesetzt. Erstens die Förderung von KI-Expertise am Standort Deutschland. Zweitens den Ausbau der Kompetenzzentren für KI-Forschung und die Vernetzung mit den Anwendungshubs. Und drittens den Ausbau und die Stärkung der Forschungsförderung zu KI und ihrer Anwendung. Wir haben bereits einiges auf den Weg gebracht, etwa mit dem Aufbau der Vernetzung unserer 6 großen nationalen Kompetenzzentren für KI-Forschung. Aber wir wollen und müssen natürlich noch besser werden. Gerade in Anbetracht der Corona-Pandemie zeigt sich das vielfältige Potenzial KI-gestützter Verfahren, etwa zur Modellierung pandemischer Ausbreitungen. Und deswegen hat die Bundesregierung ihr Engagement für Zukunftstechnologien wie KI nochmal deutlich verstärkt. Mit dem Konjunktur- und Zukunftspaket wird die Bundesregierung die Investitionen in künstliche Intelligenz bis 2025 von bislang 3 auf künftig 5 Milliarden erhöhen. Damit KI uns hilft, die Pandemie zu bekämpfen, dem Klimawandel zu begegnen, die großen Herausforderungen unserer Zeit zu meistern. Und damit KI uns hilft, am Ende auch länger und besser zu leben.
Thank you very much. Anja Karliczek was that, Federal Minister of Education and Research. And now it's time for the second session of pitches. We already learned a lot about projects on artificial intelligence in basic medical research. And now we go one step further. The next round of pitches is dealing with artificial intelligence as a tool for decision-making in medicine. The chair of this session is Professor Petra Ritter. She's Johanna Quandt Professor for Brain Simulations at the Berlin Institute of Health. Welcome, Professor Ritter.
Dear colleagues, welcome to the session Artificial Intelligence and Decision-Making in Medicine. At the beginning, I would like to provide an explanation. What is artificial intelligence? With artificial intelligence, we try to generate learning and thinking with machines. And this is not to confuse with artificial general intelligence, AGI. AGI is the intelligence of a machine to understand and learn any intellectual task that a human being can understand and learn. AGI is often a subject of science fiction. It can be also a subject of research, but today we are not speaking about AGI. We are speaking about machine intelligence and how machine intelligence can help us to solve clinical problems. And I have a short message for you. We need a culture change where data and insight and knowledge are shared for societal benefit. The European Commission plans to generate the European Health Data Space, and obviously artificial intelligence needs data, and artificial intelligence for health needs health data. So therefore, please think today how you personally can contribute to the generation of a European health data space. And now enjoy impressive presentations about artificial intelligence applications in medicine. You will see very concrete examples how artificial intelligence-based decision-making is used for clinical applications and what the latest research trends in the field are.
Thanks a lot, Mrs. Witter. And the first pitch is from Betty van Aken, Boyd University of Applied Sciences in Berlin. And again, you've got exactly 3 minutes. Please, go ahead.
Thank you, and hello everyone. I'm presenting our joint and ongoing work on outcome prediction from clinical notes at admission time. Our goal is to build a clinical decision support system that can assist doctors in their decision-making from the very beginning of a patient encounter. Next slide, please. Imagine a patient newly admitted to the ICU. The only information at hand is often in the form of a clinical note, such as this one, written by another healthcare professional. The time to process the information is limited, and certain risks might be overseen. That is where our system comes in. Based on admission notes like this, we want to learn relations between the patient's key features, such as symptoms or risk factors, and 4 relevant outcome targets: diagnosis at discharge, procedures performed, in-hospital mortality, and length of stay. This is far from trivial. The system has to detect key features in the text that tends to be noisy with many abbreviations, and then find complex patterns that lead to the corresponding outcomes. To achieve this, we base our work on state-of-the-art natural language processing, short NLP. Next slide, please. The current paradigm in NLP uses domain-specific pre-training of deep neural models. The available labeled data is usually small, so we use large corpora of unlabeled data for pre-training the model on the medical domain. But while those models know about medical language, they still lack knowledge about patient trajectories. Next slide. That is why we introduced a novel clinical outcome pre-training. With this specific pre-training objective, we integrated freely available clinical knowledge into our models and enabled them to learn about outcomes from unlabeled data, such as PubMed Central. Next slide, please. Our models not only outperform baselines, but also show to be transferable to data from other clinics. In order to gain qualitative insights, we developed a demo application for review with doctors. Next slide. You see this application here. What we found was that the model is indeed able to learn complex patterns between symptoms, risk factors, and outcomes, such as diagnosis at discharge and procedures performed. In upcoming work, we will take a look on how to improve the representations of numerical values in the text, such as vitals. Next slide. I want to end by emphasizing the importance of integrating more and more clinical knowledge into our models. This way, we can eventually build truly supportive systems for future medicine. Thank you.
Thank you, Mrs. van Aken. The next speaker is Wolf-Julian Neumann, Charité Universitätsmedizin, Berlin. The floor is yours.
Hello, it's a pleasure to talk here about brain signal decoding for adaptive stimulation in Parkinson's disease. Next slide. Deep brain stimulation. Oh, start the presentation of the animation, please. Okay, yeah. So deep brain stimulation is an effective treatment for Parkinson's disease where an electrode is implanted directly into the depths of the brain. This allows to characterize structural connectivity, functional connectivity, and the dynamics that are underlying. We have combined depth electrode recordings with also cortical recordings with implanted electrodes in human patients. And this gives us a unique window into the complex relationships between the stimulation and brain function. Next slide, please. We are now able to use implantable devices, start the animators, implantable devices to record brain activity directly through the patient's deep brain stimulation pacemaker. This allows to characterize disease-specific activity, for example, indicating the severity of the Parkinson's disease symptoms when they occur. In the future, we are going to use multimodal signal recorded with implantable intelligent devices. Next slide, please. To adapt the stimulation response, please start the animation. Adapt the stimulation response to concurrent demand that is signaled with the individual's patient brain activity. Next slide, please. Start the animation, please. Importantly, to make sense out of the multidimensional data that we can use and record in real time, we need machine learning-based decoding approaches that we are currently researching. We're comparing different methods like extreme gradient boosted ensemble methods or artificial neural networks to predict what the patient is currently needing in terms of their stimulation. We combine that with whole brain connectomics to develop a method that generalizes the individual need in real time across patients and have models that will improve the quality of life for these patients. Next slide, please. Ultimately, we believe that combining real-time brain signal decoding with adaptive control algorithms will really make an impact on DBS patients' quality of life. Next slide, please. I just want to thank all the collaborators, Timon Merck, who has done most of the work I've shown, and the clinical adaptation will be done at the Charité Neurology Department with the help of Andrea Kühn. Thank you.
Thank you very much, Mr. Neumann. The next pitch comes from Jana Fehr, Hasso-Plattner Institute for Digital Engineering in Potsdam. Hello. You can start now. Well, we can't hear you. That is kind of a problem. Can you say something again? Okay, we can still not hear you.
Can you hear me?
No, I can hear you now.
I can hear you now. Okay, weird. Okay. Yeah, sorry for that. Hello, my name is Jana Fehr, and I'm sharing our experiences from using computer-aided interpretation of chest radiography in a TB screening program in rural South Africa. Next slide, please. In Germany, we often forget about tuberculosis, but actually it is one of the top infectious disease killers worldwide. In 2018, 1.5 million people died due to TB. The WHO has set the goal of eradicating the disease by 2030, and for this, active case-finding programs are an important strategy that offer diagnostics in affected communities to detect TB infection at an early stage. The Africa Health Research Institute has established such a program called Vukuzazi in a rural area in South Africa that is highly affected by TB and HIV. Programs like this, however, have large costs for diagnostics and labor if you want to test every citizen. But now new AI-based chest X-ray interpretation algorithms, such as CAT4TB, promise to reduce these costs by selecting people who require sputum assessment due to abnormal signs in chest radiographs. And we analyzed how accurately this algorithm was able to detect TB on chest X-ray in Vukuzazi. During the first year of the study, almost 10,000 participants underwent chest X-ray scanning, and CAT4TB scored every chest X-ray from 0 to 100, 0 meaning normal and 100 meaning abnormal. A radiologist who was blinded to CAT scores and other patient data rated every chest X-ray as either normal, abnormal but not TB, or significant of TB. And people that had abnormal chest X-rays or reported any kind of symptoms were referred for sputum assessment with expert ultra or liquid culture. Among all the participants, 1% had microbiologically confirmed TB. It was interesting that only 30% of the cases showed actually significant signs of TB in their chest X-rays, according to the radiologist, and only 20% were symptomatic. These are very different results compared to clinical settings where patients mostly present with symptoms and radiologic features of TB. We found that CAT4TB had excellent agreement with the radiologist to identify TB, but it had much lower agreement with microbiological reference standards. We hypothesized from that in our community-based screening program, the identified TB cases were rather early cases with subtle radiologic features that were difficult for CAT4TB and also for the radiologist to identify. And therefore, we think that there is an opportunity to harness the power of AI to first understand the full spectrum of tuberculosis and then refine algorithms for detecting TB at an early stage. And with this, I would like to thank my supervisors at both institutes, and I'm looking forward to your questions in the discussion session. Thank you very much.
Thank you, Mrs. Fair, and I'm really impressed at how good all of you are still sticking to the time. No one has overrun the time limit of 3 minutes yet. The next pitch is by Marcel Naik, Charité Universitätsmedizin Berlin. Please. There's no one? Okay. We are still waiting for Mr. Naik. Or perhaps we could just postpone him and go over to Mr. Schwendicke. How about that? Okay, I'm just hearing that Mr. Naik is start. Okay, so we are a bit confused here. Now it is Falk Schwendicke, Charité Universitätsmedizin Berlin. Hello, Mr. Schwendicke. It's yours.
Hello. Hello, I hope you can hear and see me. I'm very happy to be here on this beautiful Saturday, and excited to present our results from the dental arena, something which is always a bit more uncommon than other stuff. And what I want to showcase you is something which is rather translational, so at the heart of this. Okay. Okay, I'm starting now because I'm hearing the regie nevertheless, but I'm talking nevertheless. It's something which is at the heart of translation. What we try to do is we try to assess an AI model which can detect caries, a disease most of you will have either experienced or heard of. And we try to assess that with regards to its cost effectiveness, because usually we see accuracy values being reported for AI applications, but not really something on the wider health and cost impact, for example, of these interventions. So our aim was to assess the cost effectiveness of proximal caries detection on a specific radiograph from dentistry with and without AI. Next slide, please. We developed a convolutional neural network. I don't want to go into any details there, where we had a number of dentists establishing a reference standard and then a number of other dentists on the test data set assessing this test data set for caries lesions. And we also had, of course, this CNN, which was a unit-based CNN, to perform on the same test set. As you can see here in the ROC curves, the model was slightly better, but not really fantastically better than the dentist. But what we found, if you could click, please. what we found is that the model was more sensitive, especially for early carious lesions. And that higher sensitivity and also the specificity values which we found were translated into another model, a Markov model, which allowed us to follow a tooth being treated in a simulated environment over long-term decades, basically, in a German healthcare setting. And we assessed using Monte Carlo simulations the cost effectiveness. And what you find here is that the differences in sensitivity and specificity, which are basically very hard to interpret for a patient or a payer, so other decision makers, translated into clinical effectiveness, tooth retention values. So we assessed how long does a tooth stay in your mouth if you use AI or if you don't use AI to detect carious lesions. And what we found was that the AI was by large more effective, retaining teeth for longer, and that's very interesting, also less costly. And that is mainly because we avoided late treatments, which occur 20, 30 years later over the lifetime of that tooth, if you detect early carious lesions and manage them appropriately. And if you translate that into, for example, the incremental cost effectiveness ratio, the so-called ICER, you can see this there at the bottom of the slide, we found that you save money whilst adding additional tooth time. And you can also see this there in this cost effectiveness plane, that the AI in blue is basically having a longer, with all the simulations we ran, a longer tooth retention time at lower cost. And that led to a 77% chance of cost effectiveness for using AI. Next slide, please. So overall, what we found is that it makes a difference using an AI tool for detecting carious lesions. But, and that is something I couldn't go into much detail here, the major driver is how these lesions are managed. We find it very interesting that it's useful using such models to demonstrate the wider health and also health services benefits of AI.
You're the first one to overrun 3 minutes, but you still get an applause.
That's nice, thank you.
And now it's Marcel Naik in the line, Charité Universitätsmedizin Berlin. I hope he's in the line. Yes, that looks good. Good afternoon, Mr. Naik. It's your turn now. Can you hear us? Doesn't look like that. Can you see us? Can you hear us? No. How about if we go over to Katharina Brauner and try again later with Mr. Naik?
Yes, I hope so too.
Now we've got the sound of Mr. Naik and Katharina Brauner in picture. But we still go to Katharina Brauner. Charité Universitätsmedizin Berlin. It's your turn now. And we go to Mr. Naik afterwards. Okay.
Thank you very much. It is an honor to present on behalf of the Open Project here at Future Medicine. Next slide, please. I am a hybrid between doctor and patient, being a doctor working in pediatrics at Charité and a digital clinician scientist of the Berlin Institute of Health. But I am also a person living with type 1 diabetes myself since 20 years. And 3 years ago, I hacked my own body. Next slide. I found documentation on the internet about a security gap on my insulin pump and how it can be used to remote control it from my smartphone and turn it into a fully functional closed-loop system, which is why I am a looper today. Next slide. The algorithm and code for these closed-loop systems are created by a community of people with diabetes that have absolutely no monetary interest in their own creation. They just want to support their peers and share the code open source over the internet. That means anyone worldwide can be their own N=1 experiment, assemble and use their own artificial pancreas at their own risk. And I can tell you that living with an artificial pancreas is amazing. Life with diabetes is nothing like it was before, and you have to imagine it like an autopilot or cruise control for blood glucose. We can sleep through the night, our glucose levels are close to the levels of people without diabetes, and it gives us back the time and energy that, the 24/7 burden of the disease previously took away from us. Next slide. For me, it was pretty clear. We need data on this, which is why I teamed up with other type 1s from 7 different locations that in their professional lives are clinicians, psychologists, data scientists, developers, social scientists, and together we formed the Open Project, which is now a €1 million project funded by the European Union. Next slide. We are translating experience-based evidence from the patient community back to academia and industry and vice versa. and examine how safe and effective these systems are, what a difference it makes to the people using them, and what barriers makes is to make digital diabetes technology available and accessible to everyone, and are working on guidelines for healthcare professionals for the safe and ethical use of open source technology, which is not licensed by regulatory bodies. Next slide. Finally, I would like to thank our amazing patient-led team. And if you want to learn more about us, here is where you can find us. Thank you very much for your time.
Thanks a lot, Mrs. Bauner. And now we try for the last time to reach Marcel Nike. Can you now hear us? We can see you, but can you hear us as well? Apparently not. Can you nod if you can see or hear me?
Mal gucken, ob es jetzt klappt.
Yes, I can hear you. That sounds very good.
Hören Sie mich?
Yes.
Sehen Sie
yes,
mich?
we can see you.
Okay.
And we can hear you. Everything's fine. You can start now. Okay, you have to start now as well. The time is running. It's 3 minutes now. But you can't hear me, can you?
Yeah, I can. Can you hear me? Can you hear me? I can hear you. Hello?
Yes, I can hear you.
Why not? I can see. I see. Hearing, I
okay,
don't.
yeah, perhaps you have to dial in again.
Hallo? Hallo? Perfect! Finally. Ja, ich höre Sie. Hören Sie mich? Ist die viel spannender?
Yes, we can hear you.
Perfect.
We can see you. You can start.
Everything's live, so
yes,
that's live.
It
okay,
is
so
live.
I'm Marcel Knight from Charité Berlin, Nephrology and Intensive Care Unit. Yeah, I'm doing. So I'm presenting the work on behalf of us. Yeah, I already started. So yeah, I'm presenting. I can hear you, and I'm also talking. What lag?
Problems here. Nike. Apparently, can we... Very sorry for this, but it is the first time we went digital, so there was things that will go wrong, and we at least did... Okay, we are stopping him. I'm very sorry, Mr. Nike, but you were on the homepage, so you presented yourself, so you are available for the 2 prizes that will be awarded after the show, or at the end of the show. And we go over to the discussion of this afternoon. We want to talk to you, and we want to talk with you. You are very much welcome to join our discussion about what the big impact AI project in future medicine needs to look like. If you want to share your comments and ask your questions, please do so over the YouTube chat function. And I am very honored to have 3 guests, 3 experts on the show who hopefully are in the line. I'm a bit curious now. The first one, yes, that looks very, very good. The first one is Professor Juliane Fluck. She is head of NFDI for Health. That's the National Research Data Infrastructure for Personal Health Data at the Information Center for Life Sciences in Cologne. Hello, Mrs. Fluck. But she apparently can't hear us. Anyway, I'll introduce the other ones. Manouchehr Shamsrizi is co-founder of GameLab, a research and development platform at the Humboldt University, and he is co-founder of RetroBrain, the world's first computer game that was accepted as a medical device. And the third one is Dr. Alexander Meyer. He is Chief Medical Information Officer and heart surgeon at the same time at the German Heart Center in Berlin, and he is in the process of founding a company called XCardiac. And I am not quite sure if you can all hear me. Perhaps you can say something. Hello, Mrs. Fluck, can you hear me? I think Mrs. Fluck can still not hear me. Mr. Meyer, can you hear me? Can you? No, no one's hearing me.
I can hear you.
Oh,
I
Mr.
don't know if you
Shamsrizi.
can hear me.
Yes, we can hear you. I wanted to start with Mrs. Fluck, but apparently she can't hear me, so there's not much sense in starting with her. then we start with Mr. Shamouzi. You are from the gaming community, and that on a first instance had nothing to do with medicine. So how do you combine these two, and how do you think can the gaming community help in medicine?
Well, first of all, thanks for having me. And I want to mention that it's not a sign of disrespect that I did not shave, but this is no Shave November. So we are raising awareness as well for men's-related pancreas cancer. So that just as a start. So many here know that's a big issue. Okay, back to the topic. I think it's not that far away as a neighborhood as one might assume. There's this basic idea of we have to take into consideration when it comes to prevention, when it comes to therapy and compliance of all these intervention, an idea of man, of ein Menschenbild. So if we want to have the patient participate in development of interventions and especially in prevention in the interventions that are offered to him or her, we need to have an idea of how mentions work. So far, the whole system of health policy, health economics, and also the doctor-patient relationship has very much been built on the idea of man that is known as Homo economicus, so to say, a very rational patient that does whatever is good for his health, and there's a logical reason for everybody to try to stay healthy and become healthy. And we know very well with good evidence that that is not how patients are or the human beings are in general. What gaming can offer on the first side, so to say, is the idea of man as the Homo ludens. Described already in the 19th century, the idea of human beings being playful and included in social communities. So any intervention might want to be as well. Let me close by quoting Oliver Holmes, who might be someone to look at, former dean of Harvard Medical School in the midst of the 19th centuries, who famously pointed out that human beings don't stop playing because they grow old and get ill, but vice versa. They start growing old and getting ill once they stop playing. So the very basic idea that we can learn from gaming beyond technological aspects of how to handle data and connect data and make sure data we use for machine learning has high quality and so on and so on. The very basic of that is thinking of patients as Homo ludens, as we say, playful, socially connected beings that are not always rational when it comes to their own health decisions.
Okay, thank you, Mr. Shamouzi. I think before we go on with the discussion, because we've got lots of time for the discussion, so don't worry, you two will have your time to talk as well. But as we had such problems getting Mr. Naik on the show, and we would like to give him the opportunity to have his pitch as well, I would like to ask Marcel Naik again, if we can have his pitch now.
Shall we stay?
Okay. No, you are staying. Please stay. Okay. Now I get the sign. We have to say goodbye to Mr. Naik. We won't get him. But I hope Mrs. Fluck and Mr. Meyer can now hear me. Can you not? If you can.
Good afternoon.
Yeah,
I can hear you well.
Perfect. Hello again, and welcome to the discussion. Perhaps we can have all four of us on the screen. That would be very helpful for the discussion. Mrs. Fluck, I would like to start with you. Can you tell me what are you doing at the National Research Data Infrastructure for Personal Health Data? How are you connected to AI and the medicine?
Okay, so the main issue on doing AI and learning these methods for medicine is that you have access to data and that you have access to high quality data, and that you can link different data sources together. And to do that, you need a kind of interoperability between different data points. So
That means, for example, that the naming in different data sets are similar, or you can map to the naming from different data sets. So that's what we are trying to achieve with the national search data infrastructure for personal health data, that we build a national infrastructure for structured health data coming from epidemiology, from public health, or from a clinical trial. So that means to make this high quality data, what we have generated, to make that available to research.
Mrs. Fluck. And Dr. Meyer, you are the physician on our panel here, the only physician on our panel here. And can you tell us something about where in your work are you using artificial intelligence? You are a surgeon, a heart surgeon, are you?
Yeah, definitely. So surprisingly, at the moment in the hospital, we are almost not using any AI-driven tool. So it is a nascent technology. It is overwhelmingly present in the research literature and in the public literature, but in clinical practice, we are not yet as far.
You're founding a company at the moment that uses AI, aren't you?
So do I. So I can tell you a little bit more about this if you like. The idea from this company, or from the project, in the beginning it was a scientific project. So the idea was, we have really a tremendous amount of data available in the hospital. And from my own observation, I observed that most of the data are not sufficiently used by the clinicians. The question of this, or the topic of this discussion, is how could an AI tool of the future in medicine look like? So my response is, the best AI tool would be a device powered by AI, but that nobody even sees it's an AI-driven tool, something like Google Maps, for instance. It's highly AI-driven, but nobody really knows it's such an AI-driven tool. So what we built is a next-generation monitoring tool which can detect complications before they even happen, and or before they are clinically manifest, and then send out a warning to the physicians, so the physicians have time to react and intervene. So this is a highly AI-based product, and AI-based research using new algorithms to detect patterns, symptomatic patterns in a highly temporal data stream. And in the end, the physicians don't even recognize the technology behind, they just see the usefulness.
Okay. Mr. Shamsrizi, I saw you nodding. Would you agree to Mr. Meyer?
Yeah, full-heartedly. Not only to the aspect that having a social entrepreneurial spin-off is a beautiful way of making scientific progress work for many people and have a real impact. But also, I think he is right when it comes to this idea of what is, for example, discussed under the banner embedded AI. There are ethical and technological and also usability challenges when it comes to that. One of that being that, of course, it should not be a black box. So if we take into consideration side effects of the example we just heard of Google Maps, we know now that, for example, cab drivers lack an understanding in some cases of how to navigate an urban environment, because they all very much rely on Google Maps handling that. That is not an argument against any of that embedded AI approaches. On the opposite, I think that's exactly the way to go. But on the other hand, that is one consequence we should keep in mind. And final thought, maybe also a very good example of things that can be learned from the gaming community, because we believe that that's why our interdisciplinary research lab was founded in the first place, that many settings, including medicine, can learn a lot from gaming, which is a discipline that has worked with AI, machine learning, and all these big words which you would need to define anyway in the first place. For many decades, and they also handled unintended consequences for many years. So I agree, the way to go is this embedded, but it should not be an uncontrollable black box. And to get there, we need to collaborate beyond the disciplines, because also air and space are fields in which this embedded AI has been worked on for many years, which might have valuable lessons for the implementation of embedded machine learning in healthcare. Yeah.
Thanks, Mr. Shamsrizi. Mrs. Fluck, would you agree that the gaming community can help very much in AI in the medicine, or in the quality of the data as well, or enhancing?
I would like to comment on the worth of this AI in medicine. So what we need for that is the variability of data, that we capture that and we get access to this data, and that's one part we want to try, that we can have data from different sources and from enough people to get reliable AI. I think that's a really important point, and the point is that currently, at least in Germany, it's very difficult to get access to this data, and that's one main point we need to change. And we can do that partly on data which is unlabeled, what we have heard in the pitches before. But on the other hand, we need also labeled data. And that's, I think, where I can also see an advantage looking in the gaming area, because annotation of data is not always a fun job to do. And we can learn from a gaming area to make a game from annotating of data and get in such a way also that it makes a little bit more fun to annotate this data. That might be a good connection between those two different areas as well.
Okay. And Mr. Meyer wanted to add something.
Yeah, I would like to discuss a little bit more the transparency issue and the black box issue, because I have a little bit different opinion about this. Of course, it's extremely important that there is research being done on this field, and it would be extremely good if there is full transparency and it's not a black box. But we always should keep in mind the single individual physician is itself a black box, and many medicines we are applying are also black boxes. What's very, very important is that we have rigorous trials which validate these AI tools. And when I talk about AI tools, I mainly mean tools for diagnostics. I don't mean closed loop systems at the moment. I think closed loop systems are another story. But for diagnostics, I think we have tools to rigorously validate those and then apply those. Because we do the same, it's basically a biomarker, like troponin or other biomarkers. There will be false positives and false negatives, but we need to deal with this, and physicians are trained to deal with this.
Okay, it's Mr. Shamsrizi again.
That's really an interesting discussion, because we are not far away from each other. So I agree with everything we just heard. My black box point was, I guess, more maybe too much really impacted by what we saw over the last months, which of course was a big issue for our community with the introduction of the DIGAs, which is something pretty new to the regulatory system here in Germany, but also worldwide. There you see that many things that are very well in place and working elsewhere, as we just heard, in relation to what biomarkers are valid, and as we heard earlier, what the data is reliable. That is something that we don't know yet if you can look at AI-based systems with the same strict logic of saying this is what works and this is what is not. Maybe also because the word AI is much too big. If you look at it from a philosophy of science perspective, you would say even the word does not make much sense in many cases, because artificial intelligence is a discipline. It's like trying to say that biology should do something or chemistry should do something. So, and when you then differentiate, you will, I believe, come up with AI agents or machine learning approaches that we can totally use in diagnostic starting tomorrow. Without having a more complex situation than we have with a doctor who might be influenced by having a bad day. It's the same with automatic driving, right, where everybody's pointing out that it might only be 98-99% working and functioning, but we never do the comparison to human beings who might be drunk or have a bad day, stressed with their family, whatever, and 98 might be actually pretty good. And then we would also have in the future more complex AI things, and there I believe more work needs to be done so that the whole DIGA idea, for example, really, can come into effect without people saying, "Oh no, it's the AI. We don't know what it is, but it sounds dangerous." And that again, that is something that you can learn from more interdisciplinary work. We're doing a lot of work in Germany right now on quantum technologies and how that translates into even better AI systems which then impact medicine. Those people have, again, a different approach. I had a roundtable in Munich a few months ago before the pandemic made these things impossible. And there was a professor pointing out that the whole idea of we collect as many data as possible over as long time as possible, so we have comparable data, would not be needed anymore once he is done with his quantum technology-based sensors, because in an instance, you will have more data from one, check-up of a patient and more reliable data than all the apps could have collected and all the sensors could have collected over the last year. So that's a new approach, and that is why I think AI is, not a good word.
Okay, we'll find a new one, perhaps, anyway. But Mrs. Fluck is next one. But before that, I would very much welcome the audience to share your comments and ask your question. You can add them to the discussion via the YouTube chat function. And please do so. We are very curious to learn about your opinions as well. And now it is Mrs. Fluck. And I would be very interested in learning how all this data work has changed due to the corona pandemic that Mr. Shamsrizi just mentioned. This urge to digitalization. Was that a search for you? Was that very important, or hasn't that changed your work? Mrs. Fluck.
Okay, so first of all, I would like to make a comment about what we need in the area to AI going. I think what we also need is the trust of the persons to share their data. On the one hand side, but on the other hand side, that we also see that this data is protected. So, and not that we share our data, especially coming from sensor and everything else, share it with Google and these huge companies, which can do everything about that, instead using this data really in a protected environment on the one hand side. On the other hand side, we have in Germany really a problem that we have a high data protection, which almost leaves nothing open that we can use the data. That is also not something we should do in the future. We need an area and space with data protection on the one hand side, but data access that we can use the tools and train the tools in future. That now coming back to the COVID-19 pandemic, so I think so we have a lot more work to do, because I'm working at ZBMed as the information center for life sciences, and there was a drastic increase in information need for the COVID-19 pandemic. And on the one hand side, the other hand side, there was a lot of actions for researchers worldwide working together, but that meant that the traditional places where you find the information was so dispersed, and also the information need, for example, most of the researchers to get the numbers for the modeling, they searched in Twitter and news to get new data before it has been published. Because normally we get our information from published research, but now that is not fast enough. And we also have seen that pre-publishing the results has one of importance in this area of COVID-19. So publishing results without a proper review process. So that's different. Another point, what's very important and for this area that the researchers agree much faster on the same variables, data items, that they can share the data. And that's a really huge improvement, what we, for example, see in Germany, all university hospitals working together to create data set in every hospital with the same variables. And Sylvia Thun is heavily involved in this work. And that's really great. And that hasn't happened before in such a fast way as it is done now.
Okay. You just mentioned this privacy protection versus amount of data available problem. And I would like to ask Mr. Meyer, because he's the one who's really working with patients, what is the acceptance of people giving their data for artificial intelligence projects, or for patients, the acceptance of patients that give or should give their data? Are they happy that you're using artificial intelligence, or that you want to use the data for artificial intelligence?
So I will answer your question in a couple of seconds. First,
okay.
I would also highlight Mr. Shamrizi's comment about the term AI, and I totally agree. And I think it's very important to know that the term AI is really misused for marketing purposes and business and research proposals. We should talk more about machine learning. That would be more appropriate. AI is a research field, as exactly pointed out before. So now about your question. So there are basically two problems. So the first thing is when we talk about prospective research, so research which is conducted in the future, from the present to the future, it's very easy to ask patients. And when I ask patients to participate in a study using AI or machine learning tools and using their data, they are actually very happy to be involved. They are very eager to learn more about this. Which data do we collect? Which data do we use? How can we apply this to medicine to solve medical problems? They are really very open. So that's not a big deal, not a big problem. A big problem is to use retrospective data, so data which is already collected. And as you know, AI or machine learning methods need a lot of data. And we can use all of the collected data from the past when it would be easily possible. But as it has been pointed out already correctly, the GDPR or the European directive makes it very difficult to do so. So I totally agree with this. It's sort of a little showstopper at the moment.
Okay, Mr. Shamsizi, he wanted to ask you something.
I would like to.
Yes, now I can hear you.
I would like to build up on what we just heard from our both distinguished fellow panelists, and I would go even one step further. That might be through my original background in political philosophy. I totally get where the idea of data protection at the level where we have it comes from, and that there is historical reasons and also very good legal and moral philosophical reasons, but that is one side of it. The other side would be, and I always wonder why this is not highlighted in discussions much more, might there be a moral obligation to use data in a much more connected and transfer-oriented way? I would argue that this obligation is at least possibly existing, which means in a free and liberal society, it should be up to the patient, because he or she owns the data, to decide if this data is used or not. As long as the system says, we will not allow you, right? There are situations in which patients get into a hospital before their data gets there. I have had my DNA partly encoded, I hope that's the right word, 2016 when I was at a conference in Stanford. They offered to do so. And since then I have that data and nobody to talk about on personalized prevention here in Germany. Now, my Persian doctor's family would tell me, you don't need to, right? Prevention is much more easy than you believe. You don't need your data to be encrypted, make more healthy food and make more sports. But still, it should be up to me to decide. And right now, the system is saying, we protect you even against your own will of using that data. And one second point is that is something really where gaming can help. If you look at esport, if you look at other gaming settings, these people are collecting data on a massive scale. They have ideas on how to handle that. They might be even able, we don't know that for sure, to collect them less biased, because there are arguments out there from a psychological perspective that people who would be socially biased in how they answer a question that someone is telling them, it might be very honest when it's in a gamified setting. So there are, because that's my role. We as a game lab believe that the Homo ludens is giving away more valuable data than the Homo economicus does. I just wanted to point that out. That's might be a potential.
Thank you, Mr. Shamsrizi. We are nearly getting to the end of this discussion round, but I would like to ask you all the question with which we started the round, and that is, what does the big impact AI project in future medicine need to look like? What is your idea, Mrs. Fluck? What do we need in artificial intelligence in the future?
So, on the one hand side, we need for sure the method development, but on the other hand side, that's what I'm standing for, is that we need the data access and we need the technical infrastructure that distributed data analysis is possible, which can use machine learning and learn and train on distributed data to generate good models.
Okay. Mr. Meyer, what is your idea on the big impact future medicine, artificial project in future medicine?
So I think I already answered this in the beginning. So for sure, to make much more use of the tremendous amount of data we are collecting daily in the hospital or in a clinical setting.
Okay. And Mr. Shamsrizi, what is your idea? How should that big impact project look like?
I agree with what we heard and also what Dr. Meyer said. I think the big impact we might be able to achieve is really personalized medicine, which starts by personalization of development of pharmaceuticals, but also ends with personalized nudging interventions. And for that we need interdisciplinarity. So that's my point. That's the name of our cluster of excellence. That is what we need, I think. Other fields have worked with AI and machine learning for long times. I believe that medicine can learn a lot, and they can learn a lot from getting some serious aims to work on instead of more internet points.
Okay, the last word is for you, Mr. Meyer. Very brief, please.
Yeah, very brief. But I think it's just was a very important statement. We need interdisciplinarity. Medical data products are highly dependent on interdisciplinary work. I couldn't agree more.
Okay, thank you. Thank you very much for your discussion partners. Thank you, Mrs. Fluck, Mr. Shamsrizi, Mr. Meyer. Unfortunately, there were no comments from the audience, so we couldn't include any, but I hope you enjoyed the discussion anyway. And get applause. Yes. Thank you. And as we had such problems getting Mr. Naik, we are now trying again. I hope it's not going to be a running joke. Mr. Marcel Naik from Charité University Berlin is hopefully now connected to us.
I am online. Good. Do you see me?
You are online, and it's now your 3 minutes. Please.
Yay! Finally, thank you. So I want to present T-Box, a project that we are doing together with Dr. Diogo Telmo Neves from the FKI. Next slide, please. Let me introduce you to the clinical problem. On the left side, you can see in green the people, for example, if they are 30 years old. In green, you can see the life expectancy of about 20 years for a dialysis patient. And if you start at the age of 30 and get transplanted, having renal insufficiency 35 years old with their remaining life expectancy, and the general population would be 50 years if you're otherwise healthy. So in conclusion, if you have chronic renal failure, dialysis is quite bad in terms of mortality, and transplantation is a little bit better. So next slide, please. Over the years, the short-term survival has been very much improving, shown in blue. However, long-term improvement is very stagnant. Next slide, please. So as you can see, there are a lot of factors in transplantation, and it's a rather complex situation, which is very good to apply AI to. So from the immunological factors, which are rejections, to avoid that, we give immunosuppression. They have side effects, and infections and cancers are a problem in the long run. Next slide, please. To tackle and detect those major contributors for graft loss, we are setting up a system. Next slide, please. The problem is the patient is mostly out of the hospital, so we don't know how he's doing. Next slide, please. So we have a transplant database, T-base in green, which has connections to other hospital systems, like the clinical information systems, where there are discharge summaries and pathologies findings and so on. Also to the lab information system, where we all have the laboratory tests and microbiology, antibiogram testing, and so on. And also the outpatient department is using T-base. So we know a lot about the patient, and the patient is also, since February, connected to the T-base, typing in his vitals via smartphone, and we can do telemedicine. Next slide, please. So we use all this data in a data science lifecycle together with Diogo Telmoneves, and we are going through it in iterative fashion, filling in the data and making it better, improving it, fitting it into the models for machine learning, and then see what comes out. So basically, we are always in a cycle. Next slide, please. So on the left side, you can see there are problems of wrong labeling, and also outlier detection is performed. Next slide, please. And we have performed 2 machine learning models as of now. One is KNN, which has a sensitivity of 87%, and a random forest, which has a sensitivity of 100%, luckily. And next slide, please. So we are incorporating lab data now to also have a time-dependent motion as to the cause of the patient. And we also want to reflect the stratification of risk for long-term survival towards the patient, that he can also adjust his lifestyle. And we want to feature like better information between the outpatient and the inpatient department. Thank you.
Thank you, Mr. Knight. And a very big applause for you, because there were so many problems with you.
Thank you for taking me in.
It was a pleasure. There is one topic that affects the lives of everybody around the world at the moment, and that is certainly the COVID-19 pandemic. That's the reason why we are here sitting and having digital problems with you. And so there's good reason to dedicate one session, the 3rd session of pitches, to the COVID-19 pandemic and to how algorithms can overcome the COVID-19 crisis. You have already met the chair of this session. It's Professor Silvia Thun from the Berlin Institute of Health. Mrs. Thun, the floor is yours.
Okay, thank you. So the next pitch is about AI and the coronavirus. So AI can build an intelligent platform to monitor and predict the spread of the virus. And this platform has to be secure and should be based on international IT standards. Besides that, AI can help to fight COVID-19 by early detection and diagnosis of the infection, delivering information about drugs, treatments, vaccine development, and prevention of the disease. So, how can your algorithm overcome the COVID-19 crisis?
And now it is the first pitch is Mathieu Chapranov from the Hasso-Plattner Institute for Digital Engineering in Potsdam. Hello, Mr. Chapranov. The floor is yours for 3 minutes exactly.
Hello, everybody. Hello, everybody. Thank you very much for welcoming me. I'd like to introduce you one project called NCOV Stats. And if you don't mind, my 2-year-old boy just around here, introduce also some material, so I hope it's more enjoyable for you. Next, please. So you can remember early this year, there was a lot of news about the new virus around, right? The virus was somewhere in China. It was far away, somewhere here. So here in Europe, no one was really aware how does it affect our daily lives. Meanwhile, we know it affects our all lives. It's a daily issue and it's a global pandemic. Therefore, we introduced nCoV stats. We created this built on our knowledge from other epidemics, for instance, the Ebola crisis in Western Africa. We created an in-memory database. We heard about that. Data is so crucial. Therefore, we maintain their all latest information about the virus spread. And then we have a very long longitudinal database now with more than 55,000 records for over 600 regions all over the globe. We created graphical data analysis tool. You see here one on the screenshots, which enables the analysis. It's free of charge. Everyone over the globe can use it. Next, please. And how did we get there? And this is somehow solving a kind of data puzzle. Next, please. Therefore, when we started, there was only a Chinese data source, the primary data source. It's called Doxy. Therefore, we tried to understand Chinese. Next, please. Then we created crawlers very similar to Google to supervise and monitor these data sources and download whenever there's new data them to our database system. Next, please. And then we created graphical tools to explore the data. It's much easier to see correlations in a graphical way. Next, please. And as we heard already, data is so crucial for decision making. We use this data also for prediction models. So can we use information here in China, what they take to fight the virus? Does it also fit for Europe? Does it fit for United States? And if you follow the discussion, herd immunity is one of the exit strategies we are following most probably. Think about that, because even the most infected countries in the world just show about 2 to 3% of their population being already infected. Therefore, this might be not an exit strategy. Next, please. Here you see latest data from Germany, and you see the spring peak. Then afterwards, we move pretty greenish. But next, please. If you add the latest data to this picture, you see it's more reddish. Here are the latest information from end of October, with more than 15,000 people per day reported as an infected case. Therefore, it's now time to react. Stay safe, wear your mask, protect your family and friends by changing your behavior. Next, please. And if you want to learn more about how we get there, please follow our data management for digital health course. It's open, free of charge, and it just kicked off last week. Thank you very much.
Thank you, Mr. Shaponov. I'm really impressed, I have to say again, how good you are sticking to the time, all of you, until now. And the next one is Moritz Lehne, who hopefully will stick to the time as well, from the Berlin Institute of Health. Hello, Mr. Lehne. The floor is yours.
Thank you very much. I would like to present the German Corona Consensus Dataset, GECKO, a standard dataset for COVID-19 research. My name is Moritz Lehne. I'm a data scientist from the BIH. So what does a standard data set have to do with artificial intelligence? Next slide, please. So AI and machine learning, of course, depend on data. And it has been estimated that about 80% of the work of a data scientist is spent on data preparation. So most of the time is not spent on the actual algorithms themselves, but on data cleaning and data collection. And this time for data preparation could be much reduced if data sets were standardized. Next slide, please. So we need interoperable and standard data. And this is important to provide algorithms with a clear data structure and semantics to ensure that analysis results are valid and correct, and to create trust in these technologies. Next slide, please. So what's the data situation for COVID-19? We already have a huge number of studies. There's more than 60,000 publications on PubMed and more than 2,000 studies published each week. And of course, it's great to have all this research, but next slide. But most of COVID-19 data are not standardized, and this makes it difficult to compare and analyze COVID-19 data across studies. And it also makes it difficult to use AI and machine learning on these data. Next slide. So to improve this situation, we developed the GECKO dataset, the German Corona Consensus dataset, which is a standardized data set that researchers can use to collect COVID-19 data. It was developed by a multidisciplinary expert board. It contains around 80 data elements from different domains, which are shown here on the figure on the right. And of course, that's the point of a standardized data set. It uses international standards and terminologies. For example, HL7 Fire or SNOMED CT. And the dataset is already used by studies in the COVID-19 research network of university medicine. So it already has some acceptance in the scientific community. And if you want to learn more about this dataset, you can have a look at the preprint published on medRxiv. Next slide. So I want to close by mentioning the people involved in developing the dataset, especially Julian Sass and Alexander Batschke. That's it. Thank you very much.
Thank you, Mr. Lehne. The next pitch comes from Kai Zacharowski, University Hospital, Frankfurt. Hello, Mr. Zacharowski. The floor is yours.
Hello. Hello, yes. My name is Kai Zacharowski. I'm from the University Hospital in Frankfurt, and I'm the current president of the European Society of Anesthesiology and Intensive Care. Every year, over 320 million surgeries are carried out. Worldwide, most of the anesthesiologists document their work on a piece of paper, as you can see on this slide. As you can imagine, this is often imprecise and takes important time away of direct patient care and has a negative impact on patient safety. In Frankfurt, we have left the manual work behind us since we use an easy-to-learn and easy-to-use digital mobile solution running on an iPad called Sandman MD, developed by the company App at Work. Next slide, please. Sandman does not require a hospital network in the operating theater. It uses a small adapter connected to the ventilator and monitor, which automatically transfers all data to the iPad via Bluetooth. Since 2018, we have documented over 60,000 interventions with Sandman. Next slide, please. We have applied for a grant project of the European Union looking for helpful solutions for the treatment of COVID-19. My department has treated the highest number of COVID-19 intensive care patients in the state of Hessen. Our aim is now to develop an intelligent tool for real-time surveillance of COVID-19 patients and smart decision-making in intensive care units. Next slide, please. The report of the Enquete Commission Artificial Intelligence of the German Bundestag drew attention to one of the most common problems in the analysis of clinical data. There are no valid data in sufficient quantity. We have overcome this problem. Every critical ill COVID-19 patient will be equipped with an iPad, collecting all patient data 24/7. These data will be transferred online to a central database and evaluated with integrated artificial intelligence and machine learning. Next slide, please. There will be a direct feedback from this AI database to the iPad of the patient. Results will be directly integrated into the treatment process. This European project is named Envision and will start next month. Next slide, please. We are proud to announce that in addition to the University Hospital Frankfurt, 13 hospitals from 11 different European countries will participate in this undertaking. Leading industry companies like Löwenstein Medical and Intelligent Data Analytics are also on board. Thank you very much for your attention.
Thank you, Mr. Zacharowski. Fabian Prasser is the last pitch from Charité University Medizin, Berlin. Hello. It is your turn now, Mr. Prasser.
Waiting for my slides. There they are. So hello everyone, and thanks for the invitation. I'm not sure whether time is ticking. Today I will present work of the BIH Medical Informatics Lab, in which we develop data anonymization pipelines to promote open science on COVID-19. And there are many ways in which AI applications can help to manage the COVID-19 pandemic. We had heard a lot about this already. However, AI methods become better the more data is available, which leads to data protection challenges. Innovative concepts are therefore needed to provide data at the rapid pace required in a pandemic. Next slide, please. And we're doing the next slide again. Thanks. LEOS is a European registry capturing data on the clinical course of SARS-CoV-2 infected patients that was established at the University of Cologne. The registry uses an innovative approach in which no informed consent is necessary, as data is collected in the form of anonymous reports. It further follows an open science approach in which anonymous data is shared with researchers and the public. For this purpose, additional anonymization procedures have been implemented which modify data to ensure that it cannot be identified. Next slide, please. The anonymization pipelines used by LEOS have been implemented in collaboration with my group in Berlin. The development process is innovative by itself because the pipelines have been developed in Berlin without access to the data stored in the registry in Cologne. Instead, synthetic data was generated and used as a basis for an iterative refinement process. For this purpose, different versions of the pipeline were developed and repeatedly evaluated using the data stored in the registry. When implementing the pipeline, we used ARX, which is an internationally recognized anonymization tool developed by our group. ARX offers a comprehensive feature set, including many different types of techniques that can be used to anonymize data in compliance with different laws and regulations. Next, thanks. When anonymizing the LEOS dataset, we combined qualitative risk assessments with quantitative approaches. Here we followed recommendations by the Article 29 Data Protection Working Party to protect data from 3 types of threats, namely singling out, linkability, and inference. To implement this, we used formal anonymization processes that deleted data based on mathematical models. We performed repeated evaluations to monitor the impact of the anonymization process on output data quality. The pipeline developed is based on the principle of hiding in the crowd, which means that the greater the number of patients included in the registry, the less information has to be removed to achieve the required degree of protection. The figures on this slide show the development of the number of records released and the differences in the case fatality rate calculated from the original dataset and the anonymous dataset over time as more and more patients were added to the registry. It can be seen that impacts on data quality decreased rapidly and that there is no significant differences between both datasets today. The work presented in this talk was done in close collaboration with several collaborators from Cologne and Munich. Thank you very much for your attention.
Thank you very much, Mr. Prasser. And even the last pitch was on time. That is absolutely perfect. And now it is time for awarding the Pitch Perfect 2020, the best pitch of today and of all the participating pitches on our platform. There are 2 categories to this prize. The first one is the best scientific pitch selected by the scientific jury, and the second one is the best innovative research pitch chosen for the first time ever by a public vote by the audience. And now the winners of both prizes have been chosen, and I am pleased, hopefully pleased, that all pitches we have seen today are back on again. And now we should be able to see them all here. Yes, there they are, all the pitches of today. And there were also many other pitches presented on our platform that entered the race and were available for both categories. And I would like to welcome those researchers as well. Hello. We start with the Audience Award. It is endowed with €500, and the prize is supported and presented by Joachim Hess from Intuitive Surgical, who should be on the screen. Hello, Mr. Hess. It's nice to have you on the show as well. But I think you can't hear me. At least I can't hear you. Okay, you can hear me, but I can't hear you. That is not good for the awarding ceremony. Okay. Perhaps you are trying to get your sound right, and we swap and do the scientific prize first. Okay? It would be not very nice if we can't hear you for the prize. Okay, good. Now I have to sort out my slides here. The prize for the Best Scientific Award and the Best Scientific Pitch was chosen by the 3 members of the jury that you already met today, Professor Ritter, Dr. Schwarz, and Professor Thun. And Professor Thun is here, so we can't have any digital problems with her right now. Hello again, Mrs. Thun.
Hello.
Why are you awarding this scientific pitch?
Yes, I just want to award it, and I just say something about why I award this. So, ladies and gentlemen, it is a great pleasure for me, a scientific director, to give a laudation for this year's scientific winners. This award honors scientists and innovative experts who made outstanding contribution to new methods in medicine. The award is intended as an incentive to continue work and break new ground. The selected contribution shows us that we can support fighting the pandemic and improve patient care if we can access data from existing systems and connected devices to read, harmonize, analyze data, and train our algorithms with fair data. So, I am happy to announce that the pitch from App at Work by Jörg Wegner, a computer scientist, and Kai Zacharowski, a physician from University Hospital Frankfurt, and his colleague from Spandau, win our scientific prize.
Wow. Fantastic. Wow. Wonderful. Super.
Okay, Mr. Zacharowski, do you have prepared a speech? I think the Oscar winners always have prepared a speech. Apparently you haven't, do you?
No, I don't have to prepare one because I'm overwhelmed. It's such a, I have to say, it's such a cool message, such a cool situation now. It's a Saturday afternoon. It's a really important project for, well, for our patients, but not only in Germany, all over Europe. And you know that I'm every day in contact with my colleagues in Italy, in France, in Spain, in Portugal, and I always get the news what's the situation there with the pandemic and how they treat the patients. And now we have this European Union grant where we can improve things, plus the prize. I'm just overwhelmed. It's really, really cool. Thank you so much. It's really a pleasure and a great honor. Thank you.
Congratulations, Mr. Zacharias. And now we go to the audience award and hopefully to Mr. Hayes, who can hopefully not only hear us, but also talk to us now. Mr. Hayes, from Intuitive Surgical, it's now your turn. Well, we can still not hear you. Okay. Now he's using a headset, I think, is he? Do you want to just get out of the line and just dial in again, Mr. Hayes? Yeah? Okay. While we are standing here, Mrs. Thun and I, we could talk about the day. Was it what you expected? We haven't yet one point of the agenda, but
yeah, I asked a question in the very beginning. So can AI and translational medicine help us with the corona crisis and support medicine? And I think we saw many, many pitches how young scientists work in this field with a lot of enthusiasm and want to improve medicine. I think, yes, the answer is yes, we did.
Perfect. Okay. How about Mr. Hayes? Can we now hear him, or can he hear us? I can't see him. I don't know if he can see us or can talk to us. If not, I would very much thank you all for participating. Okay. I'm still already thanking you all for participating, for joining us, for sharing your questions, your comments, for listening to the discussion, listening to us, joining the event, and hopefully to next year on the 7th of December. Then there will be the next Future Medicine Science Match. I know we don't drop the line, and please stay online because we are still waiting for Mr. Haas, who will hopefully come. But the word before the last word, which will now be Mrs. Haas' word, goes to Mr. Toon. Mrs. Toon. Do you want to thank you?
Yes. I like to thank many people who contributed to this conference, especially those that our speakers, our participants, our technicians, our colleagues from BIH, and Anja Karliczek and Thomas Jatzombek, who underlined the value of research and development, science and the work of researchers for people's health, Pavel Swiboda, for the exciting journey into the world of AI and brain research, Professor Dr. Juliane Fluck, who shared with us insights of NFDI for Health and the new data science platform, Manusha Shamratzi, who gave us new ideas on AI as a social driver, Dr. Alexander Meyer, who focused the debate on relevant benefits of AI at the intensive care unit, Dr. Joachim Haas, who, as an industrial partner, helps to focus on new ideas, and my colleagues Professor Petra Ritter and Dr. Roland Schwarz for sharing the sessions and preparing the Congress. To all pitch participants who continue to work on their ideas every day to bring them to the people and make tomorrow's healthcare better. Never lose your into the other. To the Tagesspiegel, which as a partner of BIH has provided with Future Medicine a platform that brings together the most innovative international scientists and research organizations. Physicians, healthcare experts, researchers, politicians, developers, engineers, innovators, representatives of industry, entrepreneurs, and investors. Thank you.
Thank you, Mrs. Toon. And now we hopefully have Mr. Haas, who can now talk to us as well. He's holding a phone in his hand.
Yeah, thank you for the kind introduction. I would say we cannot be stopped by technical features and problems. So let me start with this. Some 20 years ago, Intuitive Surgical was a startup. There were great scientific work available, but now the head engineers and surgeons of a Stanford Research Institute project on robotics decided to develop and market a robotic system to extend the reach of the human hand inside the patient's body to better perform minimally invasive surgery. At that time, many people still considered robotic surgery to be a crazy idea, but it is precisely such courageous innovations that the medicine of tomorrow needs. It is therefore a great privilege for Intuitive to present the Audience Award at the Future Medicine Science Match 2020. Without further ado, the Audience Award for the Best Innovative Research Pitch goes to Manusha Shamratzi of Game Lab Berlin for healing the Homo ludens, potentials and risks of the technologies and cultural techniques of video gaming for data-driven decision-making in medicine. Congratulations. The audience was deeply impressed by your presentation on cross-functional and interdisciplinary work combining medicine and gaming. It is obvious that at the intersection of advanced disciplines, you have the potential to achieve a paradigm shift and break out of conventional lines of thinking. In addition, artificial intelligence can actually change the focus of the health system away from health practitioners and back to patients who care about their own lives. So, you are simultaneously working on multiple elements, and this prize is well deserved. Congratulations again. Your prize.
Mr. Shamratzi, it's now time for your Oscar winner's speech.
Well, let me start. Well, thank you. I deeply appreciate. I know it's an unusual approach, but maybe let me tell you two things. The first is, well, the biggest congratulations to Professor Zacharowski and his team and partners, because I think that's incredible work. This might not be the Oscar type of answer, but I really believe that, and I hope they are making great progress. And the second is, already this idea of an audience award, I believe, is a huge step into the direction we just heard about and which we also discussed at our panel. And that is what we need to make AI work for our health, interdisciplinarity and transdisciplinarity. We have had people reaching out to us once this audience award website was put up from the gaming community, making offers like, we are a gaming studio and we have been working on machine learning for many years. How can we contribute? Someone reached out and said, we learned about that. I am suffering from an issue of mental health. Maybe we can make a game to both raise awareness and also have a therapeutic impact. So I think I agree with what we heard in the Laudatio. How could I not? And I really hope that this outreach that comes with such an award, for which I'm really grateful, will help to make this interdisciplinarity work even better. Yeah.
Congratulations, Mr. Shamsrizi. And an applause again. We all know that one of the most important agenda items on every conference and every summit is the coffee break or the cocktail party, just to meet people and to talk to people. And the downside of this virtual event is we can't offer you a coffee or a cocktail. But we still want you to meet each other and to have inspiring networking experiences. And that is why I very much invite you to join and to talk about the day on our Teams channel just now after the session or after the summit is over. All the information on how to get there is on our webpage. And I very much welcome you and I very much invite you to go there and talk to the people you want to meet and have a good afternoon. Thank you all for your patience with all the technical problems and have a lot of fun during the networking event. Thank you.